Okay, today I am going to talk about, as you can see the title, Seakeeping Considerations in Design. But before I go to that, I just want to complete one more response or derived response that I thought is important, which is actually the load part, that is wave induced load. Okay, before I come to this, now what happened? See, when we calculated ship motions, we already had load in it, because the calculation was based on mass into acceleration equal to load. However, from structural point of view, quite often a structural engineer actually would like to know what is the kind of pressure coming on the hull, what is the bending moment coming on the hull because of this seakeeping, because of the motion and because of the wave induced loads. See, the thing is that although we had this load implicit in the equation of motion, when we did basically mass into acceleration, added mass, etc., we still want to know. What the designer may want to know is basically this. He may want to know instantaneous local pressure on the hull surface. Due to motions and wave interactions. This is just for completing this part, because the load part is also important. He may want to know integrated pressure, giving right to what I am trying to say is like this, and we will just explain this part little bit. See, obviously a structural engineer wants to know what is the what are kind of local pressure coming on a hull surface, because he is going to design the scantling based on that. We have done before typically wave bending moment and still water bending moment, okay, but remember, in doing that you have never considered the ship motion effects. But here, when you are doing seakeeping, already the load part have been actually used, because when we did the calculation, we have mass into acceleration equal to force, and we actually when we wrote the equation of motion, added mass, damping, exciting force are nothing but parts of loads. So, question is that although, and then of course we found the motion, and because the section is moving, there is going to be inertial load coming further. So, all this can be calculated also as a derived response at the end, and I give a simple example of how it can be done. For example, you take, or rather let me first draw this diagram. So, if you take a section here, remember there is wave here, this section is undergoing a motion, okay. Then because of this wave, all these interaction part, there are various kind of pressure. What we have done in the equation of motion is we have mass plus added mass into acceleration plus damping plus this thing equal to force. See, this was a force, this was a force. All these force is already calculated inside. On top of that, we calculate the motions, which also may give an inertial load. So what happened with all that, one can actually calculate. An example is the vertical shear force, that V3x. It will have a contribution from I3x, x being a section, some location, minus H3S x minus H3 dx. I'll write down this minus F3x, where I3x equal to integration 0 to x sectional mass into z dot dot minus x theta dot dot dx is inertial load. H hydrostatic restoring force. I'll write. Let me write it and I'll explain to you. See what I wrote here, before I go to this seakeeping, I was just talking about load. See, I have this ship underwater, this part, right? Now, what did you do? What did you do earlier in finding out, let's say, the shear force and bending moment, wave induced? You simply considered a profile, a trochoidal profile or something. From one side, simply took the load, sectional load, to be as what? Rho GB, weight minus buoyancy. That's all that what you have taken, right? Nothing else. Okay. But here, see, in seakeeping, what we are doing, I have this section. Remember, each section, it is undergoing a motion up and down. So this has inertial load. How much? Now this is undergoing an acceleration, a section at locations x, and acceleration vertical is going to be z dot dot minus x theta dot dot, because that is a vertical velocity. So acceleration is this. So if you integrate that mass into acceleration, you get this sectional inertial force. Now, so obviously, with the vessel is undergoing heave and pitch, so each section is undergoing a vertical acceleration, which is arising because of heave and pitch combination. That is what we have done earlier, isn't it? Z minus x theta is the vertical displacement and therefore acceleration with the dot dot. So you have this. Then remember, because it is going up and down, I have got a displacement which is given by Z minus x theta into local beam. That will give me my so-called AWP into Z, the so-called the hydrostatic restoring force, additional part. Remember the additional part, because the rest part is balanced with the mass part, so we are not taking that. This is the additional load coming because of ship motion. Okay. So this is my additional part, unbalanced between the buoyancy and the sectional buoyancy. Then we have got this added mass and damping load. Remember, added mass and damping are arising, which was also a part of a load, because the ship section was moving, it was radiating waves, and that has altered the pressure field, and that pressure field again acts as a load. And of course, we have the exciting load, because what is happening, if you look at this equation of motion here, we actually obtain the equation of motion by added mass and damping force, that is given by this part, that is AZ plus this part. This is basically added mass and damping load arising because of a certain pressure field created. This was an exciting load arising because of again a certain pressure field created because of the wave structure interaction. This was actually load arising because of the hydrostatic restoring force. So, and then of course, mass into acceleration would be a so called your inertial force. So, all this can be taken. See, it is already embedded, but structural designer may want to know not only vertical shear force, then he might want to know vertical bending moment. It will be simply integration of this into x. So, it can be obtained like that. So, and not only that, you can also give him, because each point we will know the pressure. So, the entire pressure distribution also can be given. So, this is what typically we do. The final part I said that when you do Seakeeping, you know, there are many outputs coming up. One also want to know, especially structural designer, what is my wave induced bending moment considering Seakeeping, considering the motions. And this is not what you have done earlier, if you remember, because in earlier wave bending moment calculation, in fact, there is no dynamics involved at all. Simply one assume that the wave profile is stationary and we need to get toroidal profile. The difference one can make out easily, that this is obviously the correct thing if you have a Seakeeping. And obviously, when you did the Seakeeping calculation, you already have all of them with it. So, when you do Seakeeping, you have found out A, B, C, F, M. So, and then found the motion. Therefore, at the last stage, you can again reassemble and get this values. That is typically done. That is what I am trying to say. So, this is kind of the last part. Now, I am going to come back to what I was today's last lecture, and this Seakeeping part is Seakeeping consideration in design. Now, you see here there is an observation now that typically, you know, in design, people have not been paying enough attention of Seakeeping, but there is a present consensus that this should not be so. One of the reasons is because for computing Seakeeping initial stages, you really don't need to have the line span or the hull geometry so accurately. All you actually require is an approximate shape. For example, if I knew the section shapes purely by means of local breadth, local draft and section area, I can actually determine sectional added mass, etc. What I am saying here is that in order to do elementary Seakeeping calculation or initial Seakeeping calculation, you do not have to have very exact hull shape. Even if you have that, you are anyhow going to make added mass damping calculation, which is an approximate. So, therefore, there is a general consensus that it should be actually made a routine part of design. Anyhow, so having said that, the reason it is said because one don't want to expect some surprise after the design. You find out there is some you know, some characteristic you don't like. But having said that, let me tell about these considerations. Other main thing that comes down to is like this: habitability. Of course, you know what is habitability. There should be certain criteria about certain limits of motions that makes it habitable. For example, if accelerations are exceeding certain amount, you find very uncomfortable, which actually happens very quite often, especially if the natural periods are low. Then my natural periods are low, then frequency is high, then acceleration becomes much higher. Like it happened to a small boat, people will always come and complain that they are uncomfortable because it is accelerating much faster. You see, if natural period low means what? It is basically going to oscillate at a lower time. So, it will come back from this to that at a lower time. So, acceleration is much faster because it is omega square into displacement. So, habitability is concerned with various parameters. Next comes operability, which of course is a level higher than habitability, because what happened, even if it is not very habitable, your mission requirements must be met. You have a ship, it has a gun mount and it is supposed to fire. Now, if certain motion exceeds, you are not able to operate. Let us take an aircraft carrier. You cannot take off and land beyond certain like motions of the deck. So, that gives an operability criteria. You have an offshore research vessel, you cannot do an experiment, lower some equipment down if there is excessive say roll motion, etc., etc. Then of course come survivability. This of course that having said that even this I mean that this is related to extreme weather. Well, excuse me, your design should be able to survive in certain extreme motions, weather, storm condition, certain say sea state 7 or 8, it should survive. So, again survive means what? It should not have certain amount of again seakeeping criteria beyond some limit. So, all this basically what it says is all this will translate down, we will write down in next one. They are affected by this following, the parameters that affect these things are obviously I am just writing down, going to write down. They are going to be, well, basically you can slowly write down. Actually, we do know all these things, but I think I still write for completion part. Actually, what we wrote is that more or less almost all, you see, the derived responses that we talked about and more, they all affect the design in some sense. Now, the question is, see, this is all, if you think you will be able to understand that not all affect equally, it all depends on the kind of design, kind of mission requirement, etc., etc. Here comes the question, that what is happening is that most of the design, now we are talking in the design, you have to have a specification that it should not exceed this, it should not exceed this, etc. How do I have this specification? There is no uniform rule for that. And I just give two examples, but let me first give you one example first. That you see, one example, for example, of this criteria is given like that. Just to have an understanding. Once again, I tell you that these are the factors that affect. What is that what we require? We require to now assess a design or consider seakeeping aspects in design even in the initial stages, let us say. So, I must have a criteria specify that, look, my design should not exceed so and so, so and so, so and so, etc. some criteria, acceleration must not be more than say 0.2 g, etc. So, this criteria of course there is no uniform basis, which is what I am trying to say. That depends on the mission requirement, that depends on the person. There is no rule right now, because habitability etc. cannot be made a rule. You might find comfortable up to certain acceleration, another person may not be able to. A cruise ship might have a different habitability criteria compared to a naval ship. Okay. So, having said that, there are some criteria of response that you have to establish and then find out how I can assess a design. So, this typical criteria might look like that. This is a criteria for a naval ship for helicopter operation. Say for a frigate. So, it may look like the criteria: location, just to give an idea. So, here say pitch, it says it may look like that: location, here they have got different level, in this case launch, recovery, just to give an idea, support. This it says for all of them 3 degree, but roll for this is for roll, it says for launch it is 5 degree, recovery 5 degree, support 3.5 degree. Then deck wetness, where at FP, what is this? 30 per hour maximum. Slamming, this is deck wetness. Okay. I will give a right example at 50% LBP from, that is 4 foot 15% beyond, 20 per hour. Then vertical acceleration, it says where? At breach. So, 0.4 g. Lateral acceleration, same place, 0.2 g. Vertical velocity, where? At helicopter point. Touchdown point, it says launch time is none. This recovery time is 2 meter per second and support time is none. See, what I am saying, this kind of table you have to, one has to make, or a designer has to, when you are designing it, the owner has to specify that for my ship I want this criteria. Okay. So, there are two things that we will talk about. One is this, that criteria that is given. Now, what you do? What one has to do is, therefore, after that, calculate at all possible C states, or if the environment is given at those C states, the characteristic from seakeeping and then irregular C calculation, all these values, say when they say pitch not exceeding 3, he will actually be mentioning significant pitch or average pitch, some value of pitch in a C state. Okay. Then having done that, one makes what is called a polar plot. That is the most interesting thing. So, you will calculate for various C states. For different C state, one will calculate all these criteria. No, that you, for example, you find out how many times slam occurs. Then we make a polar plot. Now, polar plot looks like that. There is a circle here. For order of merit. So, we have here various speeds. Actually, it is a radial plot of V versus theta. So, these are various V's and these are various mu's or headings. Okay. What you do is that people will find out. See, let us take an example. Bottom slamming at a given location should not exceed 20 per hour. Okay. Now, you find out this is for a given C state. Say C state equal to say 4, some C state. You have to repeat that for different C state, and this is for a particular say response slamming. So, what you find out is that say this slamming 20, it does not, there is a boundary there. If the waves are, this is actually say 0 degree here and this is 180 degree here, okay, this is one, rather you start from 0, 90, 180 like that, this is the angle you can make out. It turns out that say let us say something like that, it is this region, that is this combination of V and mu. If the shape is within that, then my slamming becomes less than 20 per hour. In other words, supposing my shift speed was say this was actually 6 knot or 8 knot, 10 knot, 12 knot. So, if it is say 10 knot and this angle or whatever, then I will find out my slamming is more than 20. So, this gives me an area, that means over this operation zone up to now operation zone is defined, maximum speed is say 12 knot here. So, I have this circle as the operation area, right. Now, I find out that in that only in this area essentially my slamming is within the limit, design limit, whatever was specified. So, this was one criteria. Now, you will have to for C state 3. So, what you have to do is to put on that all other criteria. See another criteria roll, for example, it might be some other area. Then what happened? The two are combined only in this area, which is a common area to it. That means only in this area either both roll will be less than 5 degree or whatever and slam will be less than 20 per hour. So, this kind of plot, now having done all that, you find a common area. So, this common area as a percentage of the total area would give me the merit, that means that the merit of the design for that C state is so much percentage. That means so much percentage of time, that is you can say performance index. That means in C state 4 my operation criteria would be satisfied, let us say X% of time, or that is not time really, that is the order of merit, that is X percentage gives you an order of merit. See, I give an example here, actual example of a ship that we carried out in C state 5, 3 and 5. So, here let me just read this from this, I do not know if that is possible here, okay. I just write down that. See here a particular ship that we carried out where the parameters were given like that. It says vertical acceleration at bridge 0.4 g, deck wetness 30 per hour, slamming 20, almost same thing, roll significant amplitude is 10 degree, pitch, this of course sounds very high, but an actual ship data I am telling, this people have specified this. Excuse me. Remember one thing, that it is not necessary to include all the parameters that we have mentioned earlier. See, in Seakeeping parameter can be large number, which we have mentioned earlier like this. All are not necessary to be mentioned. You know, an operability index or whatever the criteria may be specified for a few, but typically you will see a common thing: vertical acceleration, slamming, deck wetness, roll and pitch. This normally become a very important criteria. Most of the design will give actually this. Vertical acceleration becomes very important. For a defense kind of craft, they will also limit vertical acceleration at the equipment location, because if you know, and where the ground mount, if it accelerates, it undergoes very high load, you may not be able to operate something. Now, having said that, see, there is a this design, maybe only little bit you can see that see, this is a different, just for example I am giving polar plot for different criteria. The first one, it shows the full hatch, means that in C state 3, this was for C state 3, I am just trying to give an example. Vertical acceleration, entire zone is operable, no problem. That means entire zone my vertical acceleration is coming more than this thing. Similarly, slam per hour, in this case entire one is operable. Actually all this excepting what we are getting is this one roll. It turns out that roll you can operate at this region excepting this white. See, remember, it's interesting, these regions are actually beam C region. That means when the waves coming from the side beam, naturally there you expect much more roll. So in this is only C state 3, very low C state. So it can operate excepting when it is within this, means when it is 90 degree, 90 plus minus say 10 degree or so, probably it looks like here 100 degree to something like 60 degree for whatever the amplitude. And similarly here, okay, that's all. And now when you combine all that, when I combine, put them all together, the combined operable region becomes this. So here what happened, if hatched part by this part will probably become something like 70%. So 70% of the combined V and mu I am able to operate. Okay, but now this is C state 3, go to C state 4, 5. Immediately big difference. See here, if I were to plot this set, these two together, this one is vertical acceleration. Now my vertical acceleration here, C state 3 I had entire part, but C state 5 I find that this much I cannot operate. What is this? Very high speed at head wave condition, not able to operate. Next one, here I cannot operate over this region, that is this is actually slam per hour, too much of slamming here. This pitch, no problem, 5 degree actually too large a pitch, but deck wetness same thing, I cannot operate. Then more interestingly, roll, this big area I cannot operate. So when I combine that all that two together, you see for this particular C state, it turns out I can only operate at this range, the entire range I cannot operate, because at least it does not satisfy the criteria. That means in C state 5, such a rough weather, only following condition I can work. Okay. So now this gives me an order of merit for individual C state. Now what is the next step? The next step is also interesting. What you do, now we know the ship is going to go to a given area. So I know that it is operating from A to B, and I know here that C state 3 occurs 60% of time, 4 occurs say 20% of time, 5 occurs say 10, well 80, 15% of time, and say 6 occur 5% of time. So what I do, I simply multiply those factors with that 0.6 into 0.7. So I can end up getting an overall merit of the design based on this. This is exactly what is done for evaluating a design, you see. But obviously what you do, what one can do is that typically in a design of seakeeping, you cannot design the ship to make sure that its roll is going to be 4 degree. What you do is that you can only do a design because too many parameters are involved, and find out, having done the particular design, what is its performance criteria finally. So the point is that initially you can iterate the design. If I have a design tool available, as I said, I don't require the geometry fully. All I require is see, when you are doing a lines plan, if you recall, you end up actually making a section area graph, SA graph, and you end up getting another one, what you call this water plane area graph, right. Essentially you will be knowing each section in a design, local breadth B, X, local draft, which of course becomes typically a draft, and section area. These 3 parameters, normally you are drawing a section shape. In fact, with these 3 parameters only, one can estimate using Lewis form and other forms, added mass and damping. And then there are programs like strip theory programs available by which you can estimate RAOs. And once you have RAO, of course, you can always go to the algebraic process of determining response in irregular waves. Okay. So therefore, at the design stage, I have done a design in one of the loops, and at that particular loop point, when I have frozen this, I can easily do the seakeeping calculation and find out the entire criteria. So you know what I am saying, therefore, is that it can be easily done. The only problem, of course, is that you have to have a seakeeping kind of program tool available with you and should be able to run it. Now that is not always very simple, because The common tools are like strip theory methods, etc. They are not, like you cannot do them in a calculator, tabletop calculator. It's a program that you must have. Many of the design what I should say uh, programs, the design suites are having Seakeeping program as a part of it. Okay, so this is one part of the design. Now, as I said beforehand, there is really no fixed rule regarding what is acceptable, etc. But some empirical formulas have been suggested by some people in a broad sense to evaluate design. One of them I will just mention is called Bell's criteria to or Bell's Seakeeping rank. As I said, once again, there is no uniformly accepted standard or empirical formula to tell what is a design with good Seakeeping characteristic or some numerical measure, but some have been suggested. One of them is in a preliminary design is, I want to mention here, Bell's is a very crude way of actually telling Seakeeping rank estimator. This is applied for naval hull. What it does is that he presumes, and it has been found that Seakeeping depends on only a few parameters. One is water plane area, forward of CWF, air into B. One is water plane area, aft top midship. Now, this is a new word, cut-up ratio. Actually, this is a typical point in a hull that is defined C by L, where this is actually close to this is a point defined in a particular, like in a defense vessel. Space is there. C V P F equal to V F by A T. Similarly, this aft of so with that, with these parameters, actually this is just, you can see that he has come up with a formula which says like that. It's a very simple formula. This is only to give you an idea regarding that there are some formulas available. It says Okay. See, this is only to give you a very rough idea. Really speaking, it is not very like important. It is a very crude, rough idea to evaluate rank. What it means, you know, I'll tell you. Supposing you are doing an initial design, okay. So you are changing parameters. So you have two kind of forms. Now you want to rank them. Which one is better compared to which one? You can use such empirical formula to tell that, well, this is going to be slightly better because it will have a larger R, slightly higher rank compared to the other as far as Seakeeping is concerned. Okay. So this is, there are some similar formulas available, but it is recommended that one don't use it as such if you have a tool of computing Seakeeping at hand. And today at 2010, at this time, every shipyard or everywhere you go for design, you should have in the design spiral a good Seakeeping estimator based on strip theory or something. Okay. And then of course, many are, now see, having said that, this gives you an overall idea, but there are many other parameters also that may be important. I will see, what we said here is that you have done a design, then how you are kind of seeing is performance. But if I will just talk next few minutes only on, as a designer, a feeling about which design parameter affects which Seakeeping criteria in which form. That means if I increase length, do I get a better heave motion, lower heave motion, etc. That is effect of different parameters on certain responses. That will give an idea, because that way, for example, shape, forward, should I make a V shape, should I make a U shape, should I make an inward shape, which is good. See here, of course, the detailed shape has not been mentioned. I will just mention briefly that part, very briefly, you know, length, breadth and all these parts, because we really cannot tell so much. Now effect of here, just one second, let me see this pen. Length, just broadly, see, very simple, slicker form, longer and slicker form. Obviously, when you say for a given displacement, for a given length, less displacement, which means what? Finer form, obviously, making it longer but not too shallow. It's also obvious, you see, if you, you know, like I can, you can just think intuitively. If you have a shallow draft vessel, now wave effects, wave forces. See, if you look at this vessel, wave, you know, it goes like that. The parameters, the wave effects go like parabolic. Now, if you say that the effect, the load that comes at this level is of this magnitude, but if you have a deeper vessel, you will have a much smaller. So the exciting force that tries to push it up and down, which causing you pitch and heave, is going to be less. Okay. In fact, one of the reasons of semi-submersible has been that you bring down this buoyancy part lower and lower. If you do it lower, the exciting force that comes on that is less, because, you know, as you go further deeper down in water, okay, the wave kinetics reduces. The wave kinetics is all exponentially reducing. So if you consider a point here, the wave acceleration, which of course after all decide the kind of force acting on that, is going to be small. So deeper draft vessel will obviously expect less excitation in vertical plane. Now, here in lengthwise seakeeping, it turns out that if you make it longer and finer, but that don't make it too shallow draft, you have a overall better seakeeping criteria. Okay. Now, like that we can keep going. Beam, not much effect. There is some effect, but we are not going to go this thing. Draft tree. Now, this is actually these are general observations, you know. Actually, what I want to write is more than block coefficient. See, this is what up again. The waterplane area affects primarily the bending moment, or that makes sense basically, because in waterplane area comes down, you have a much restoring force, so the larger bending moment comes out. Okay. Now, the other thing is freeboard, and this is important. Okay. Now, this part you see here, forward part, should you keep large flare, like maybe the deck here, or should you keep smaller flare? Now, the point is that, see, this flare, increase in flare normally will increase the slamming. That's obvious, you know, especially this flare slamming, what they call slam at this region. This is also connected to your so called you know, like U shape and V shape. On the other hand, the point is that freeboard by itself don't have much effect generally as far as the section shape is concerned. So, what is happening is that this is actually a question of you know, like judicious choice. Should you take typically the U shape and slightly V shape, has their competing effects. In V shape, the slamming is larger, basically bow flare slamming is larger, but bottom slamming is smaller. U shape, the bottom slamming is larger, there is no bow flare slamming. Bow flare slamming means slamming coming at this region. Okay, now the question that comes is that how do I choose that? That depends on, it comes out from other design considerations. So there is no really hard and fast tool that you can tell. Now a very nice example was given here that I wanted to just mention, that suppose you have to do a aircraft carrier design. Okay, now a aircraft carrier, small size, you want to have large deck area because of the large, now if you have large deck area, you are looking at large flare. If you want to have large flare, then you must find out whether, in fact, you will find most of the aircraft carrier have a large flare. But if you have large flare, then you must make sure that the ship has lower vertical motions, because if so, they are going to have a large, slamming here. So therefore, it's a question of kind of combination. Bottom flare you can afford to have large, provided the vertical accelerations are small. Because if it is small, then load is going to be small. In other words, if I were to tell that look, flare is necessarily increasing slamming, that is not true, because that depends on the motion itself. Now if you have a low, then the motion may be somewhat low. So therefore all these criteria are, as I said, there is no hard and fast rule. Okay, what it comes down is that most important factors therefore is basically length. Beam is not so important, but draft is important, because if you have a very shallow draft, you have bad motion. Forward sections become somewhat important for deck wetness and slamming point of view. Water plane area coefficient is important from bending moment point of view. Block coefficient is not very much important. So more or less one knows what are the parameters, but the most important, of course, of all of them is to ensure that you have a natural period that is not very much close to the resonance, and to make sure that your pitch and heave natural period do not coincide close by. You want to have a separation, because we have seen earlier that the natural periods for typical shapes are very much in the vicinity of typical wave that exist. Okay. So therefore, one of the important point was to ensure, even if you space them by 2 seconds or 1.5 seconds, that is good enough. But it should not be like natural heave and pitch period should not be within 0.25 seconds. That is one point. Okay, then just another 1 minute. I mean, this is the last class for as far as seakeeping part is concerned. I just want to tell you one more thing, that yesterday we talked about like speed loss. One more thing that the captains quite often do when one travels in ocean. See, we have seen that if there is a speed here, V here, basically it comes down in various sea state with respect to sea states here. But point is that sometimes, this is just the last part, is that sometime the captain has to deliberately lower the speed, because it might be having excessive some motions. So he might have a cutoff here somewhere. That means although the loss is here, what is called voluntary speed loss, he has to deliberately lose the speed, because if you did not, you end up finding that it is slamming excessively. So therefore, obviously you don't want to do that, but this is what is known as voluntary speed reduction. That means you deliberately reduce the speed, otherwise you are finding out that you are having very excessive motion. So this is also another part of seakeeping which is important when actually you are going on a rough sea. Okay, with that, actually I am going to close this part. That means seakeeping otherwise is a very large topic, but we had only limited hours. So with this present lecture, the seakeeping part of this course is over. Next hour we are going to spend on maneuvering. We will start maneuvering from next hour. Okay, so with that I will close this.